So we went over the Canvas page a little bit yesterday. And just to clarify a couple of things, there is a course schedule linked here. It's the third tab under the logistics. And so if you click on the course schedule, I think I showed this to you yesterday, but it takes you to a page that has all of the assignments and sort of the pacing for what we're going to be covering. Everything is, of course, ballpark. So we may or may not get to things on, any given day. I know we still have a little bit to finish up from yesterday, but I did want to remind you that in particular, this 2.1 solution curves, I did post a video as well as notes for that. It's about a 16-minute video. It's not very long. It's not necessarily a concept that we're spending a lot of time on, but I think it is helpful just to like visualize what do our answers even look like. All right, so on your own time, watch that video. Again, it's about 16 minutes. There are also notes that go with that, so you can take a look at that. And I think there is one question on the homework due this week that deals with the solution curves. Okay, so if you're looking at this being like, on the quiz or on the homework and saying, wow, we never learned this in class, I just wanted to remind you that there is the video posted for 2.1, so you can watch that on your own time before the quiz or before the homework as necessary. Okay. Other than that, are there any questions that have come up for folks in the last 24 hours since we have started? All right. Well, if there are no questions right now, then we can go ahead and finish up 1.2. Okay, so we have like one more example to do from 1.2. We're going to spend most of today on 2.2. All right, so 1.2 and 2.2 are our main topics for today. So you can find those notes on the Canvas page, all those blank notes there, and then all of the videos and complete notes will be posted after class. All right, so let's jump right in. Boop, boop. Ah. Okay. Also, yesterday I forgot to stop and start the video in between the two sections, but typically every video will be per section. So we'll stop this at the end of 1.2, and then there'll be a separate video link for 2.2. So you don't have to like go back and forth during the video to try and find the part you need. Okay. All right. So yesterday we talked a lot about finding degrees of differential equations and talking about their linearity. And then in the second part of class, we looked at solutions for initial value problems, okay? And so we worked through a couple examples. One we sort of did together, and then I said the other one, I would encourage you to check that one on your own time and make sure that it is indeed a solution, okay? And we just have one last example left here. So we did that a little bit for example 2 as well. And for example 3, I said we would come back and finish part B today during class. Okay. And so one of the things that you might notice here is that in our equation, hey, this is our solution, we actually have not just t, like the variable for time, but we also have this c sub 1 and c sub 2, okay? And a lot of what we do in differential equations is actually trying to find the constants that fit a particular solution, okay? And so what we're gonna do right now is we're gonna take this proposed solution, and we're going to plug in the initial values to try and find exact values for C1 and C2. And so after we finish part B, we're going to be able to write this equation, but instead of C1, we're going to have a number. And instead of C2, we're going to have a different number. Okay. So let's take a look. We've got one initial condition, x of pi over 2 equals -2. And we've got a second initial condition, x prime of pi over 2 equals 1. And so first, let's begin by substituting in the x of pi over 2 equals 2 into this particular solution. So when we do that, we'll get x of pi over 2 equals c sub 1 cosine of 4 times pi over 2 plus c sub 2, oops, yep, sine of 4 times pi over 2. And we know from the initial condition that that equals -2. Okay. And so before we plug in the other initial condition, let's simplify that what we have here first. Okay. And so let's see, C1 cosine 4 times pi over 2 gives me 2 pi plus C2 sine of same thing, 4 times pi over 2 gives me 2 pi, and we get -2. Okay. I see a question in the chat. Can you explain initial value versus initial condition? Okay, so initial values mean that we want to find the C1 and the C2, whatever those constants are. But the initial conditions are usually what's given to help us solve the initial value problem. Does that make sense, Denise?
Yes, thank you.
Great. Sorry, I didn't see your question for a bit. Okay, so let's, as a refresher, go back to our trig values. Anybody happen to remember what cosine of 2 pi is? Cosine of 2 pi. Yep, that is going to be 1. I know it's been a while probably, so this is going to be 1. What about sine of 2 pi? Yeah, that's going to
0.
go. Perfect. All right. If you do end up taking either PDE or ODE, knowing those trig values, like especially the ones that go to 1 or 0 or -1, will be super, super helpful. Okay. But this means that we can clean up our expression a little bit. In fact, we can write this as C sub 1. That's the only thing left on the left-hand side equals -2. Okay, so we found one of the values that we want to find. When we go back and write our equation, we'll be able to put a -2 everywhere we see a C sub 1. Okay. Now, the reason why we have 2 initial conditions is because we have 2 constants that we need to find out. And so we're going to use the second one along with that first derivative that we found yesterday to find the other constant. Okay. So I'm going to grab that other equation, x prime of pi over 2. And everywhere I see a t, I'm going to plug in pi over 2. So -4 C1 sine of 4 times pi over 2 plus 4 C2 cosine of 4 times pi over 2. Okay. And we know, according to our initial condition, that that's going to equal 1. And so before we substitute in our C1, let's see what else cancels out, all right, as we replace those values. And I think we'll end up with -4 C1 sine of 2 pi plus 4 C2 cosine of 2 pi equals 1. And when we go back to those trig values, we know sine of 2 pi is 0, cosine of 2 pi is 1, and we'll end up with all of this is going to go to 0. And the only thing left over here is 4 times C2. And you'll notice that we didn't need to plug in C1 equals -2. And a lot of the cases that we'll be handling, that's going to be true. Okay, so I would plug in your initial conditions, see what shakes out before you plug in the constants that you already found. Okay, and so if we do a little bit of manipulation, we get C2 equals 1/4. And so in order to write our solution of the initial value problem, we're just going to copy our general solution, but everywhere we see a C1, we're going to put -2, and everywhere we see C2, we're going to put 1/4. Okay. And so I'm going to zoom back in. We'll write our final solution as x of t equals -2 cosine of 4t plus 1/4 sine of 4t. Okay. And so all that means is of the multiple solutions that we have possible for these initial conditions, this will be the solution. Okay. We're going to spend a lot of time finding both the general solutions, which is right up here, right? So the one with the C's in it, we'll find the general solutions, and then we'll also be asked to find solutions for an initial value problem, okay? All right, are there any questions on 1.2?
Yes, I have one. Did we go over boundary conditions at all?
Ah, that's a great question. So for us, we're going to focus mostly on initial conditions, but boundary conditions kind of work the same way, where you're given some sort of information and it will help you find some of the unknowns in there. Okay, so initial conditions and boundary conditions can be used to find the constants that we don't know. I think that boundary conditions make a little bit more sense when you get to something like partial differential equations, because you're looking at actual objects and like the boundary of when things, where the heat transfer is or where there might be a wave motion. And so in those cases, we'll start to bring back some of the boundary conditions, okay? But for right now, the process of initial conditions and boundary conditions will be very similar for us, all right?
I also had a question, and this is part of the discussion post when I was researching, just trying to get a better grasp. So for having a second order differential equation, you need two initial conditions. Is that just to find the constants?
It is, because if we look at this one right here, right, example 3 is a great example. It says, consider the differential equation, and we're given x double prime plus 16x equals 0. And so from yesterday, we know that that x double prime is a second order differential equation. And check out, we had not one, but 2 constants we needed to find. If we have 2 constants we need to find, we need 2 sets of initial conditions.
Could I just ask something as well? So I'm glad Dave brought this up, because I was confused on the discussion as well. So I guess what's throwing me off is, with one initial condition, couldn't C2 be any value, right?
Yes. And so if we want a very specific solution, we need to make sure that we've solved for both of the unknowns.
So we're looking for a unique value for C1 and C2.
Correct.
Okay. All right. Thank you.
You're welcome. Okay. So if you have not taken a look at the discussion yet, I would encourage you to do so, because we're going to go through examples in class. But what I'm trying to hit with the discussions is like some of those concepts and things that we should anticipate about what information we might be given. How do we know which method to use? So that's where a lot of that discussion will happen. Okay.
Sorry if that just ruined it.
No, you're absolutely fine. I think, this is our first week. Let's kind of figure out the flow of things. I'm actually really glad you brought it up because if someone waited until the last minute to look at that discussion and had that question, they were kind of out of luck, but I think you set them up to be successful. So. All right, so I'm going to go ahead and stop this recording.